Renowned physicist Michio Kaku sheds light on what truly lies within black holes. Surprisingly, total annihilation isn't what awaits us in the heart of these enigmatic cosmic giants. Instead, we uncover a realm so astonishing, it leaves us in awe. But how did Kaku come to understand this mesmerizing secret? How do scientists typically explore such a deeply intricate subject? And could we, perhaps someday, witness the mysteries hidden in black holes with our very own eyes? Roughly 6 years ago, astronomers around the world celebrated a historic achievement. In April 2019, using the Event Horizon Telescope, they managed to capture the very first image of a black hole. This groundbreaking photo revealed the gravitational behemoth residing at the core of the massive galaxy M87. Though this galaxy is about 55 million light-years away, there's something important to remember. What we see in that image isn't the black hole itself, but the chaotic effects it has on its immediate surroundings. More specifically, the image displays the glowing matter spiraling into the black hole, what scientists call accretion flows. These are drawn in by the black hole's immense gravitational pull. The term black hole reflects their defining trait, complete invisibility. The reason nothing, not even light, can escape once it crosses the event horizon. So what causes this extreme phenomenon? To grasp why black holes pull everything into oblivion, we need to look at their incredible density. These cosmic giants pack a tremendous amount of mass into a minuscule space. For instance, if a black hole had the same mass as our Sun, its event horizon would only span about 6 kilometers. In comparison, the Sun itself is nearly 1.4 million kilometers in diameter. A black hole with Earth's mass would be no bigger than a marble. Are black holes truly just engines of destruction? Interestingly, the black hole in that famous image is located at the center of its galaxy. That raises a vital question. If black holes are so destructive, why hasn't this one devoured everything around it? The answer lies in how close objects are to the event horizon. Unless something crosses that invisible boundary, it remains safe. Outside this critical zone, black holes behave much like any other massive object. They can be orbited peacefully. Today, it's widely believed that nearly every galaxy harbors a supermassive black hole at its center. These titanic entities play a central role in shaping galactic development. Our own Milky Way is no exception. It contains Sagittarius asterisk, a supermassive black hole captured in an image for the first time in 2022. Also by the Event Horizon Telescope, the term supermassive indicates just how much larger these are than our Sun. While Sagittarius asterisk is about 4.2 million solar masses, the one in M87 reaches a staggering 6.5 billion. Yet, compared to some black holes observed in the universe, even these seem modest. One such black hole, named TON 618, is estimated to be 66 billion times the mass of our Sun. Despite their astonishing size, we still don't fully understand how such massive black holes form or what might lie inside them. Michio Kaku's insights into black holes reveal his gift for explaining complex ideas in an accessible way. Known for his work in string theory, Kaku described the black hole images as nothing short of the holy grail of astrophysics. For him, the mystery of what lies beyond a black hole's event horizon is among the most fascinating puzzles in modern science. So, what would actually happen if someone were to fall into a black hole? Would the extreme gravity tear them apart? Could they reappear in another time or even another universe? One particularly fascinating, if speculative, idea suggests that falling into a black hole could lead through a tunnel into another cosmic realm. Kaku describes this theoretical tunnel as a white hole, the mirror image of a black hole, where matter isn't consumed but expelled. A black hole and a white hole together form what's known as an Einstein-Rosen bridge, more commonly called a wormhole. While wormholes are valid mathematical solutions to Einstein's equations, no physical evidence of them has yet been found. The same goes for white holes. Both remain entirely theoretical. What these two have in common is something called a singularity at their core region of infinite density. But while black holes pull matter in, white holes would theoretically push it out, in theory, matter. Falling into a black hole could emerge elsewhere via a white hole, perhaps even in a different universe. However, these mirror-like structures would not be traversable from the outside in. Kaku likens this to the world behind the mirror in Alice in Wonderland. Just as Alice steps through a looking glass into a surreal reality, wormholes could represent doorways to alternate dimensions or timelines. In non-rotating black holes, described by the Schwarzschild solution, the singularity is a point. In rotating black holes explained by the Kerr solution, the singularity becomes a ring. This ring-like singularity exists because the black hole spins so rapidly that space and time twist around it. This deformation prevents matter from collapsing into a point and instead forms a loop. This Kerr ring, in theory, might be passable. Instead of facing infinite gravitational force, one could move through the ring and emerge somewhere else, perhaps across the universe, or even in a different era. It would function like a cosmic mirror, connecting to realms through a wormhole. But how realistic is this scenario? Could wormholes be used as shortcuts through space or even time machines? According to Kaku, while the idea is thrilling, it's also riddled with uncertainty. Many scientists argue that wormholes, if they do exist, could be inherently unstable due to quantum effects and intense radiation. In such a case, attempting to travel through one would be fatal. Another issue lies in the limitations of our current theories. Einstein's equations break down at the center of black holes and wormholes. His theory of general relativity only accounts for gravity, not the quantum forces that govern particles and radiation. Kaku believes that to solve this problem, we must develop a unified theory that combines both gravity and quantum mechanics. So-called theory of everything. One of the greatest scientific revelations of the 20th century is that all physical laws seem to fall under just two fundamental frameworks. Einstein's theory of gravity describes the behavior of the vast galaxies, black holes, and the universe itself. Quantum theory governs the tiny subatomic particles and radiation. Ironically, despite their fundamental rules, these two theories don't fit together. Even the brightest minds have struggled to reconcile them. Kaku calls this one of the universe's greatest paradoxes. Each theory operates under its own principles, but they refuse to merge into a single coherent model. Still, a promising candidate has emerged: superstring theory. Superstring theory proposes that subatomic particles are not point-like, but instead tiny, vibrating strings. Just as the vibration of a violin string produces musical notes, the vibrations of a superstring produce different particles. These vibrations also influence the fabric of space, giving rise to black holes, wormholes, and other exotic phenomena predicted by Einstein's equations. However, superstrings can only vibrate in 10 dimensions. This allows enough room to include both gravitational and quantum forces. According to Kaku, previous efforts to unify nature's forces failed because they were confined to four-dimensional spacetime. He compares this to a fish living in a pond. For the fish, the world has only two dimensions, length and width. It has no concept of a third dimension above the water. Yet, when it rains, the ripples give the fish indirect evidence of the higher dimension. Similarly, humans cannot see higher dimensions directly, but we may observe their effects, like gravitational waves. According to this theory, light is simply a ripple in the fifth dimension. And as we add more dimensions, we gain room to unify more forces. Still, critics point out a major flaw: we haven't been able to observe these extra dimensions in experiments. Currently, we describe every event in the cosmos using four coordinates: length, width, depth, and time. But proponents of superstring theory suggest that the universe originally had 10 dimensions at the moment of the Big Bang. Over time, 6 of these dimensions may have curled up into tiny, unobservable forms, leaving behind the 4 we're familiar with today. In summary, while black holes remain one of the universe's greatest mysteries, they may also hold the key to unlocking the next great leap in our understanding of reality, from hidden dimensions to alternate universes. The journey to uncover these secrets is far from over.